Welcome back to another video. I'm not gonna call this lecture because it's not definitely not a lecture. So we're gonna stick with the term video. Anyway, nonetheless, it's gonna be informative to understand. Anyway, you are probably wondering why, like, what does this have to do with what we're gonna do? Like, it's gonna be digital electronics. Why do we have to know how to do things in binary? Well, the thing is that while in analog electronics, so in electrical engineering, standard electrical engineering, with the course that I have made, we were just doing with certain kind of values in the continuous time. Right now in digital electronics, we're going to be dealing with discrete time, and in particular, we're going to introduce the elements, the circuit elements, which are going to work only in binary. So this is why this is extremely important to know and remember. So let's introduce with the building blocks of electrical engineering. There are essentially a few circuit elements, and I'm just going to introduce the gates before I talk about transistors and stuff like that. Just want to introduce the gates. So those gates are called gates because they can either, they're going to give you something, they're going to take something in input and give you something in output. And the building blocks for this are going to be the AND gates for starter. So I'm going to talk about the AND gate. So the AND gate, what's an AND gate? How does it look like? Well, it looks like this. If we have two inputs, the AND gate looks like this. So the two inputs are going to be A and B, and the output is C. Now, what does an AND gate do? Well, an AND gate is pretty straightforward. If both the input A and B are true, then the whole statement in the output is true. If one of them is false, then the statement is false. I know that this doesn't actually kind of make sense, but bear with me, because this is electrical engineering for digital circuit. So what's true and what's false? How do we define those states? Why does it matter? Well, we can define two states, okay? And we can define a positive logic, which is the one that we generally use. So in a positive logic, we're going to have V min, voltage min, and V max, and also I min. Well, let's just call I low, not min, because this is right terminology, and I, well, let's just call high low and high high. So V low, V high, and I low and I high. Okay, so in a positive logic, V low is going to be 0 and V high is going to be 1. Same thing applies for I, so I low is going to be a 0, I high is going to be a 1. Aha! Now we know why we were bothering with all those binary conversion stuff like that. In digital electronics, we're going to have only two possible values because we're going to work in binary. I'm going to have 0 if the voltage is low, current is low, or 1 if the voltage is high and the current is high. So, keeping in mind this, we can write something that is called a truth table. Now, what's a truth table? You're about to see it. Just prepare. If you write A and B and C as the output of our AND gate, which is this one here, okay, and we can say, okay, let's try with different combinations of the input. If we try with 0 and 0, okay, this is a NAND gate, AND, okay, AND. If the input, both the input A and B are both 0, then the output is definitely going to be 0. If the input A is 0 and B is 1, then the output is still going to be 0 because both of them have to be 1. If instead the input of A is 1 but the input of B is 0, then C as the output is still going to be a 0. And lastly, if both of them are 1, then the output is going to be 1. So, as I said, we can think about those as true and false, or as, in positive logic, as I said, about voltage and current. So, if in one of the input, if both of the input are 0, so voltage low or current low, so there isn't much happening in here, then the AND gate is not going to let current go through, except for very low, something really low. If one of the inputs is 0, so it has low voltage, low current, and the other one instead is, has a high voltage, then the AND gate is still not let anything go pass through. If instead A has high voltage but B has a low voltage, then the AND gate, and write it AND gate, is still not going to let anything go through. But if both of them have a high voltage, then the AND gate is letting something go through and it's going to let 1 in the output, which says that it's going to be a high voltage as well. So this is the first logic gate. I'm going to introduce another logic gate. It's going to be OR, the OR gate. There we go. What's an OR gate? Well, an OR gate looks like this. Yeah, there we go. Should have. Doesn't really look like. I'm bad in drawing those, but anyway. Some people even call this basic, but it's not the right thing. So we have two inputs, A and B, and an output C. And this is an OR gate. It's like the AND gate, but it has, this curve at the bottom here. So, just like for the AND gate, we can write our truth table for this one. And I think you can actually figure out what it's going to do. So A and B are the input, C is the output. I'm just gonna do the same thing. So 0, 0, 0, 1, 1, 0, 1, 1. Now, or it's just gonna say, okay, it's fine. It doesn't really matter for both of them to be, 1 to be at high voltage. I'm just gonna let something go through if at least one of them has an high voltage. So if A is 0 and B is 0, then the output is going to be 0 because none of them have an high voltage. Now if A has a low voltage is 0 and B has a high voltage is 1, then the output is going to be 1 because, OR says at least one of them has to have a high voltage. The same applies for the contrary. So if A is 1 and B is 0, so basically if A has high voltage and B has low voltage, then C is still going to be high voltage because, conditions are satisfied. So it's still going to be a 1. And lastly, it doesn't really matter if both of them are, with high voltage. The more, the merrier, as we say. So if A has an high voltage is 1 and B has an high voltage is 1, then C is definitely going to have a high voltage and be 1. Now, there is something, because when they were building those gates, they were saying, okay, the AND gate pretty straightforward, is fine. The OR gate, it has a little bit of ambiguity. The thing is that, yeah, sure, at least one of them has to be 1. And we said that if both of them are 1, so high voltage, and the output is going to be 1 with high voltage, which is fine, as we said, the more the merrier. But what if we don't want that? What if we want an output to be 1 only and only if at one of the input is 1 and the other is 0, but not if both of them are 1? Well, they introduce another gate, which is called the XOR gate. Oops. Okay, I'm just gonna use another piece of paper. So, the XOR gate. Whoops, there we go. Now, the XOR gate looks like this. Whoops. It looks like a NOR gate, okay, but it has this one here, the curve, but it's not connected to the, to the OR gate, which was this one here, okay, because the OR gate itself is not connected to it. There we go. So this is XOR gate, A, B, and C. Why do we call this one XOR? Well, XOR literally just means exclusive OR, which is pretty straightforward. It basically says, okay, this is just like the OR gate, except for the fact that it's exclusive, so it doesn't include the case in which both the input are 1. So if we write the truth table, just like before, okay, so with A, B, and C, in here, A, B as the input, C as the output, what do we have? Well, you can just find out 0, 0, 0, 1, 1, 0, 1, 1. So if both of them are 0, okay, as the input, so A is 0, B is 0, so both of them have a low voltage, then the output is going to be 0, because the XOR actually wants at least one of them to be 1, so high voltage. So if A is 0, low voltage, and B is 1, high voltage, then the output is going to be 1. Just like that, if A this time is 1, but B is 0, so A is high voltage, B is low voltage, and the output is still going to be 1. But notice here, if we have both A and B to be 1, so both A and B are with high voltage, then C is not going to have a high voltage, it's going to have a low voltage, because this is not an OR gate, it's XOR gate, it's exclusive. So it's like an OR gate, but it excludes this last case, in which 1 and 1 is not what we want. We don't want 1 here, we want 0, we want a low voltage here. Then we have some other gates. We can do all the kind of stuff with this case, but anyway, we have other gates. We can just negate them, and just say, okay, what if I want the same thing as the AND gate that we have here, but I wanted negative, so I wanted the opposite of what the AND gate does. Well, we can do that, and it's called a NAND gate. So a NAND gate is essentially a not AND gate. So it's like a gate, as like an NAND gate, but with a not. What happens when we say not something? Like, what happens when we say like 1? Okay, this is 1 in binary. What happens if I say not 1? Well, not 1 is 0, and not 0 is 1. So this is what happens when we say not something, when we negate something, when you say not something. And we generally write it with this line on top of the number, the binary number. So how does it look like? Well, a NAND gate, so a not AND gate, looks exactly like a NAND gate, just like this, but we're going to have just a circle here right before the exit. This basically means that we're going to have, the input go through the AND gate, and then whatever we get with the output, before it actually reaches the output, we're going to invert it. We're going to negate them. We're going to invert it and say, okay, this not this result and not this result, and invert, and just like I did here. So this is a NAND gate. We have A and B, and this one is the output C. So if I write the truth table for this one as well, we're going to have A, B, and C. Again, 0, 0, 0, 1, 1, 0, 1, 1. So what happens? Well, we want just easier to think about what will happen if we have an AND gate and then we invert the output. So an AND gate will say that both A and B has to be 1 so that the output can be 1. Okay, so if A and B are 1, the output is 1. In this case, they are 0, so the output will be 0, but if it's inverted, is 1. Okay, so the output will be 0, not, inverted is 1. Well, let's just write 0 not, just for the sake of, and it's 1. just to make our life easier, okay? So if both A and B are 1, in this case they are not, because A is 0, B is 1, but both of them have to be 1, then the output is 0, but we're gonna invert it, so the output is 1. Again, A is 1, B is 0, both of them need to be 1 with high voltage, so the output is going to be 0, but we have the inverse, so we're going to invert it, and we're going to get a 1, and lastly, both of them are 1, so both of them are with high voltage, the output will be with a high voltage, so 1, but we have a NAND gate, not a NAND gate, so we have this inverse here, so we're gonna invert this 1 here, which becomes a 0. So the output of this will be, this one, with all 1 except for the 0 here at the bottom, which is exactly the opposite of this one. The AND gate, normal AND gate, will have all the zeros except for the last one, which is 1. In this case, we have all 1 except for the last one, in which we have 0. So this is the truth table for the NAND gate. And we can do the same thing with the OR gate. We can take an OR gate, just like this one, and invert it and say, okay, not the output. So we called it, of course, a NOR gate. NOR gate. Because it's a negative NOR. A negative OR. Sorry. Okay. So just like this. So a NOR gate. How does it look like? Well, it's just like a NOR gate, but with a NOT, so with a circle before the output. So a NOR gate actually looks like this, like a spaceship. And then we have a circle here, the output. This is C, A, and B. And this is a NOR gate. Now, if we write the truth table once again for this gate, what do we have? Well, just do same thing, 0, 0, 0, 1, 1, 0, 1, 1. Those are the inputs, the all possible inputs. What do we get as an output? Well, an OR gate basically says that if at least one of them is 1, then the output is 1. But we have a NOT here, so it's going to be the inverse of that. So 0 and 0, both of them are 0, so none of them is 1, so the output will be 0, but we have an inverse, so 0 NOT, which is 1. Then 0 and 1, okay, so at least one of them is 1, so the output will be 1, inverse, so 0. 1, 0, so at least one of them is 1, so the output will be 1, inverse, so the output will be 0. And lastly, 1 and 1, both of them are 1, we are fine, we want that, it's an expected behavior because we have a NOR gate, so a NOR, like an OR gate, but negative, so the inverse. So 1 and 1 gives us 1, inverse, which is 0. So our final result will be this behavior. And of course, I know that you are probably screaming, yeah, we can do the same for the exclusive OR, right? Yes, that's exactly right. We can do the same thing for the exclusive OR. So in this case, it will be basically an XNOR gate. So an XNOR gate would look like this. Whoops. Like an exclusive OR gate, okay, as we said before. It's the exclusive OR, but then we're going to have the circle before the output to invert whatever we get as the output. So A, B, and this is the XNOR gate. So the exclusive NOR gate. If we write the truth table for this one as well, so A, B, and C, with A and B as the inputs and C as the output. What do we get? Well, so the inputs are still 0, 0, 0, 1, 1, 0, 1, 1. Now, what do we get? Well, the OR gate basically says that at least one of them has to be 1, but it clarifies that we don't want both of them to be 1 and give 1 as the output. So 0, 0, none of them is 1, the output is 0, but we have a NOT, so 0 NOT, which is 1. 0 and 1, at least one of them is 1, then we have 1 as an output, and we say not 1, which is 0. 1 and 0, at least one of them is with high voltage because it's 1, so the output is 1. We say not 1, so the output is 0. And lastly, we have 1 and 1. Both of them are 1, and we don't want them to be 1 as the output. So the output will be 0, but we have a not, so not 0, which is 1. So this is our final expected behavior. So yeah, this is pretty much it. With those gates that I just draw here, so with the AND gate, an OR gate, a XOR gate, a NAND gate, a NOR gate, and a XNOR gate, exclusive OR gate, we can design our circuit and make many things. Really, many things. And later on, we're going to see other things like flip-flops and latches and those kind of stuff. But those things, those guys here, are the building block of digital electronics. So in this case, it's worth remembering now. So I hope this is clear, and I hope it helps. As always, stay tuned, and bye for now.